Okay, for this third lesson we're going to be looking at the compound angle formula and how you can use it in trig identities. But first we're going to have a quick look at something called polar coordinates. So instead of xy coordinates, we'll look at polar coordinates. So here in GeoGebra I'm just going to make a slider for this value a. I'm going to make it go from 0 to 2 pi to represent a whole circle. So this can be our angle if you like. So it's just a value of the angle that I can manipulate with the slider. You can do this yourself if you want. Right, and I'm just showing it sliding along the x-axis. Right, now as you can see, as the value of the angle moves along the x-axis, the value of the function, the sine function, moves up, and I've got that line moving up and down to show you the height of the graph at every point on the angle. So as you can see, at the angle being 3.14, the height of the function is back down to 0. And what I've got here is a cosine value of the function at the same time, but written as an x coordinate. So the y coordinate is represented by the sine value of the function, and x coordinate is written as the cosine value. Now if you pay attention to how these two lines are moving together, each one being one of the coordinates, the point where the two lines overlap, you can see that moving around the screen in a anti-clockwise direction, that can be thought of as a pair of coordinates. So I'll show these as dots. So if each dot, B and C, are the two separate coordinates, the point where the lines overlap is the pair of coordinates that represents an x and y coordinate, or in this case a cosine of the angle and a sine of the angle. So instead of representing your coordinates as x and y, we're representing them as two functions of the angle. Okay, so I'm going to try and make this a set of coordinates, x coordinate being cosine of the angle and the y coordinate being the sine, and you can see that dot where the two lines overlap moving around. Now if I remove, I'll animate it, but if I then remove those other lines, you should be able to see that in fact everything else is gone. That's just a line moving in a circle, and thus we've got our coordinates written in terms of an angle. Okay, so looking at this proof of the compound angle formula, just say we had this angle here. I've broken it down to different parts. So the lines FG are perpendicular to AB, DE is perpendicular to AB, DE is perpendicular to HF, and FD is perpendicular to the line AC. So we've got the angle here, alpha in red and alpha in black are actually the same angle based on these assumptions that we've made. So using this diagram here, we're going to try and prove the compound angle formula. Okay, so if we've got this angle here, and the previous one was denoted theta, so we've broken it down to two parts, alpha and beta, then sine of alpha beta is equal to the opposite over the hypotenuse, SOHCAHTOA. So here's the hypotenuse and here's the opposite. So I can write sine of alpha beta as the lines DE, the opposite over AD, the hypotenuse. Now looking at this picture here, because we know these perpendicular lines, HE and FG are equal. So when I break the line DE down into DH plus HE, DE can also be written as the lines DH plus FG or GF. So I can then break my SOHCAHTOA ratio down to be sine of alpha plus beta is equal to the lines GF plus HD over AD. So that's my opposite broken down in half over my hypotenuse. Okay, if we just take a quick look at the alpha down the bottom, the black alpha, the hypotenuse for that triangle is the line AF. And if we look at the same angle, the hypotenuse for the red alpha is the line DF. So if we look at the triangle, those two separate triangles. Now, you'll see why we use these values in just a second. And just a reminder that this is quite complex and not something you'd probably be expected to know how to do off the top of your head in an exam. It's mostly just for your interest or for your understanding, seeing where it comes from. There's a shorter proof in the back of the textbook, but it isn't as visual as this. So here's my two fractions to denote my opposite over hypotenuse broken in half. If I just write this again, but I multiply by the top and the bottom by the hypotenuse for the black alpha, then if I multiply by AF over AF, I'm not changing anything. I'll do the same to the second fraction, FD over FD. I haven't changed anything. So far all we've done is algebra based on what we can see in this diagram here. So just a little bit more algebra. If I rearrange these two by switching the denominators, then I can write that as GF over AF times AF over AD plus, and do the same thing for the second pair of fractions. Now why have I done this? It's all just algebra to try and get to a proof, but because we've not broken any algebraic rules, this proof will hold. So we can see that the line GF is the opposite and the line AF is the hypotenuse for this angle alpha. So therefore GF over AF is equal to, from SOHCAHTOA, sine of the angle alpha. Doing the same thing for this triangle just here, the hypotenuse and the adjacent side, you can see that AF is the adjacent over AD, which is the hypotenuse. So this part of the fraction is equal to cosine of beta. Right, moving to the triangle with the red alpha, the hypotenuse is DF or FD, and the opposite is, the adjacent side is the line HD. So that means we've got this fraction represents the cosine, so SOHCAHTOA, of angle alpha. And the final one we'll be able to do is FD over AD is the sine of the triangle with angle beta. So what we've done now is a visual proof. It was long and you don't need to know anything but the end result, and this will be in your formula sheet just there. That's the final proof based on what we just saw before. So pause this if you want to look at it for a bit longer. Otherwise we'll just move on, because here's the sine graph, and I just want to make one more point. Sine of negative the angle is equal to negative sine of the angle. Right, we'll use this result for the rest of the formulas. And also, unlike the sine graph, the cosine graph is symmetrical about the y-axis. So if you flip that over to the left, it would look just the same. So because of that, if you took the negative of the angle, it really makes no difference. It's just the same thing. So cosine of negative the angle is the same as cosine of the angle. Right. So just pause here if you want to look at the formulas a bit more. The tan one has a bit of a different derivation, but those four there, the two cos and two sine ones, follow from those results. So this last one here, you often see it in your formula sheet written like this. That little plus minus followed by the minus plus means the minus plus says you do the opposite of what you had in the first half. So if I've got cos of AB, that will be written as, well, I'll show you in just a sec. So here's an example. Cos of AB over cosine A times cosine B equals 1 minus tan A times tan B. And I'm going to try and prove this trig identity using my compound angle formula for cos A plus B. I know that's equal to cos A cos B minus, because we've got cos A plus B, minus sin A sin B. So I can switch out the numerator on the left hand side, and I'll start by working with the left hand side and try and prove the right hand side. So just switching out the numerator, the top part of the fraction, I've got cos A cos B minus sin A sin B over cos A cos B, and I can split that in half around the minus part. So this here, cos A times cos B over cos A cos B is just 1, minus sin A over cosine A times sin B over cosine B. Well, because we've seen previously that tan is equal to sine over cos, proved that in a previous lesson, we know that sin A over cos A is equal to tan A, and sin B over cos B is equal to tan B. I'll just bring that one minus down, and there we have it. That there is the right hand side. So using our compound angle formula and the rule about tan, we've proved it.